Okay, so now, I mean, if you guys can look at this, you can open that CPP file that's in US Studio. So this is going to, so this is it here. This is going to define the logic behind those actions, how people interacting with the contract are allowed to update the data in the USAO database. So
the top one is, let me play student. Right, so the top one is it writes from its own table. It tries to write to its own table, right? Action is right. Yeah. Require authentication from, so it asks for its own private key so that it can actually write to the table.
We're going to go through all this right now.
Oh, okay.
Yeah.
Okay,
yeah.
okay.
So we're going to go line by line like we just did. Yeah. So here we have that high action, right, from our header file, which is where it's declared. So here we have that function, and here is where we're going to actually implement the logic of it. So the first thing that we do is we call a function from the USAO library called requireAuth, and this checks that the transaction has a digital signature corresponding to this account. So that means only the from address put in there can modify, can call this action. So this transaction here, we saw it before. What we do here is we create a digital signature of it. Now let's say we sign it by a different account's keys, John's account. That's different from the from here. If we now send this to the blockchain, what will happen is the API running on the node, it won't even actually add this to the blockchain. It'll reject it straight away. It pre-executes it, and then it'll send it back straight away saying there's an error. So it doesn't actually ever even hit the protocol. And that frees up the protocol from not having transactions that fail on it. It is possible to get a transaction to fail onto the protocol, but the API tries to limit that as much as possible, and that improves its throughput by not having lots of failing transactions in the protocol. But yeah, if you really want to, you can put transactions that will fail into the protocol. You can bypass that, but there's not really much point. So these APIs try to be clever and try and not put failing transactions on the blockchain. If you're connecting to an API that you think is lying about your transaction shouldn't be failing, then you need to connect to another node or run the software yourself and connect to it, and then you can really have full proof that what you're doing is actually failing. So remember before we defined that table, so this is the type def. Now we're going to use that variable. We're going to use that type. So that type is here, and we're going to create a variable with it. Okay, a variable called messages. And the constructor for that variable takes two arguments. So this creates the variable. So that constructor is here. It says who is the what is the account that we want to look at that has these tables in it, and what is the scope. Okay, and what we've done here, this is get self. So this is going to say we want to look at the table in our own account, and we want to use that same scope as well. Like I said, let's not worry too much about scopes. It's a bit of a confusing topic. They're not used for what they were supposed to at the moment, so the best case is to use the same table name as you have scope. So this now allows us to look at the table in this accounts database. So that scopes, I'm not going to cover that. So now we run a query on the tables in the database, on that particular table we created. So we created a table, it's here, called messages. So now we want to run a query. So we use the multi-index table API that's exposed at this variable. We run find and we pass in what user we're looking for. So this is the from variable from that was passed in as an argument. And this queries the table against the users. Remember, users was the primary key. And checks if this table already has a value here corresponding to that user that called the function. Now, if it didn't find a value in the table, then we're going to create a new record for it. If it did find it, then we're just going to modify that row in the table. So this is part of how iterators work in C++. This is a standard iterator template. If you're not familiar with it, that should be okay for today, but that's generally how this works. This is standard C++ iterators formats. So what we do, if it does not exist already, if we can't find that user in the table, then we add it there. So we use the InPlace API on that messages table. The InPlace API will add a new row to the table. And that InPlace API has two arguments we pass in. Firstly, the name of the account that's going to pay for the data in the table, and a lambda constructor, a function that defines that the data. So this is that data structure with the user and the text. These are the two variable types in that table. So don't get too mixed up by this. It is a bit confusing. This is just the structure. Just go with it. So somebody actually has to pay for data in this table because there is a finite resources on the server. We're going to go into that resource accounting in a bit, but basically you have to define who will add data to that table, and they get billed for it. Make sense? Any questions? More or less. Yeah?
No, I'm trying to compile the information.
Compiling. So what's important here is whoever pays for the data has to be either the account itself that controls the data or the transaction sender. So this is different to most other blockchains where only the transaction sender can be billed. So in Ethereum, Bitcoin, whoever sends the transactions get billed. In EOSIO, the code owner, the contract owner can also be the one that takes the cost. And that gives that flexibility. The contract code defines who gets billed. So that allows the contract to take that cost, allows them to build like freemium business models if needed. So it gives that flexibility. That's defined in the code. If it's not the account with the smart contract or an account who's authorized the transaction, then this will fail. It has to be one of those two. So if we could not find a row in the table corresponding to the user, then we're just going to if we can find a row in the table corresponding to that user, then we just modify it. We don't want to add a new row. And so this is the API here. We're using that multi-index table API with modify. So here we put in the iterator that was returned by the find. So this query return an iterator. This points to the row in the table that it found. Here, when we modify a row, we have to tell it which row. We use that iterator. Again, we have to specify who's paying for the data change, and a similar kind of lambda updater, which tells it which data to modify. Here, we don't need to modify the user value. We just need to change the message. So that was it for the high function. So now you can see basically this high function lets anybody with an account add a message to the table. They can add it to their row of the table, and they can modify their row, but they can't add to anybody else's row, and they can't modify anybody else's row. That was defined in that require auth statement. Yes?
Can we do a stupid exercise with this so that we...
Yeah, we're going to do that in a sec.
Okay, so that I write to his, or not write, yeah. I write to mine, but I can read his message.
So the other function here, this is a useful function for development. This basically goes through the entire database and clear wipes it all. This clear function. So firstly, the only one that can call this function is the contract's account itself. So me or you, we can't wipe this table, but the smart contract owner can. So they may need to do that. Yep.
So these tables are off-chain. Because if it's on-chain, it's immutable, right? You can't make any changes.
No, so this is an important point. So the question was, these tables are off-chain. So what is immutable in a blockchain is the history. The transaction ledger is immutable. The current state of the blockchain, the data in the database, that can be changed depending on these smart contracts. You can never change the history of the blockchain, but you can update whatever the state defined in these smart contracts is as defined in the smart contract.
Right at this moment, but as soon as a transaction has been completed, then it becomes part of the history, right?
Yeah, and you can always see that happen. You can see if somebody updated the contract. They can update the logic and who did it.
Can you see if somebody called the clear function?
Yes, you can see who called it. All of that. That will never be lost. So this kind of clear function is not typical to put in a production deployment, but it's useful for development. What you can do, so as your smart contract needs new logic, maybe there's a bug, maybe you need new functionality, you actually change the smart contract's logic. I'm going to show you guys that in a bit. And you might need a migration function that will migrate data from one table structure to a different one. And then all of that's also done all on-chain, those transactions, so you can see who's done it, who's created the migration function. So all of that is immutable. But the database itself changes according to the smart contract logic. Does that answer the question, I think? Yeah.
Yeah, I think, yeah, once.
Yeah, history immutable, current state is defined by the smart contracts. So here there's just one new API that we didn't see before, which is the arrays API. So that deletes a row in the table defined by the message array it points to. So this allows this function here to go through and delete everything in the database in that table only. So here we're only looking at the table for this contract. We can't point this to another account's contract data. It doesn't have write privileges, so it can only control the tables in its own account. The review of the implementation. So firstly, actions can define authorization, who is allowed to call specific actions. They can check other conditions and throw errors, which we didn't quite see, but you can imagine it's certainly possible, whatever kind of conditions you need to check. It then uses the multi-index table API, which has a create, read, update, and delete functionality to update the tables in its own database, in its own account. It can also read from any other account's tables if needed. And then it can also execute other contracts. So it can call another contract's actions as needed. We haven't seen that yet either.